This lesson is going to focus on equilibrium special cases and specifically calculating the reaction quotient, which is going to tell us whether a system has actually reached equilibrium or not. So we've dealt with questions that have systems that have reached equilibrium, and we've done the math to solve for a variety of things. What we're going to look at now is what is happening just before a system reaches equilibrium. And we know that just before it reaches equilibrium, the ratio of products to reactants is not constant. Okay, so what we mean by that is if we were looking at a concentration versus time graph, and we saw some product increase over time, and we saw some reactant decrease over time, we know right here we've reached equilibrium. Well, now maybe we're over here, okay? And if we're over here, we want to know, well, have we reached equilibrium or not? We're going to be testing out, exactly what's happening in these systems. So in order to do that, we need something called the reaction quotient. And we use this to determine if the system has already reached equilibrium. It will tell us whether it has or it hasn't. And if it hasn't, then which direction will the system shift in order to reach equilibrium? So does it need to make more reactants to reach equilibrium, or does it need to make more products? So the reaction quotient is very, very similar to the KEQ. It is set up exactly the same way mathematically as the KEQ, but the difference is it uses instantaneous concentration. So we're going to tell you, we've taken a snapshot of a system. We know the concentration of the reactants. We know the concentration of the products. Those are the values we're going to use in these mathematical equations. And because we're using instantaneous concentrations, what this means is that we do not use an ice chart because we don't know whether the system is at equilibrium. You use an ice chart if it's reached equilibrium, and we're just checking this to see if that's happened or not. So this is kind of a nice thing. It means your math is going to be easier. So once you solve for the reaction quotient, which is Q, you're going to compare it to the KEQ value. And if the Q value is smaller than the K value, then what we know is that K is larger and the reaction has to shift to make more products, right? A large K means that we're favoring the product side. So we have to make more products in order to reach equilibrium. If the two values are equal, we're at equilibrium. But if the Q value is greater than K, that means that K is a smaller value, and that means reactants are favored. So then we're going to favor the reactant side in order to reach equilibrium. So let's set up an example of this. So here is the reaction to make ammonia. It's called the Haber-Bosch process, and that's just named after two men who came up with this reaction, and it revolutionized the fertilizer industry and agriculture. So it's kind of an important reaction. So at 500 degrees C, the value for KEQ is 0.40. Okay, so we're going to keep that off to the side. I might even just write it down here so it's front and center, okay? And this is the number that we are trying to compare to see whether we've reached equilibrium or not. The following concentrations of gases are present in the container. So they know that the system is closed. They know that there's a little bit of reactants and products, but again, they're not sure whether it's reached equilibrium. So it's a little snapshot of what's happening at this instant in time. So they tell us the concentration of nitrogen, they tell us the concentration of hydrogen, they tell us the concentration of ammonia. They say, is this mixture at equilibrium? So remember we said that we're going to set up a reaction quotient, which is exactly the same as setting up a KEQ, which means I'm going to take the concentration of my products raised to the power of whatever the exponents are, or the coefficients are, divided by the concentration of reactants, again, raised to the power of whatever the coefficients are. So in this case, my products are ammonia, and I raise it to the power of 2. This is an N. And then I divide by the concentration of nitrogen to the power of 1, times hydrogen to the power of 3. Again, no ice chart here because we don't know that it's at equilibrium. We're trying to check it out. So we use the instantaneous concentration. So make sure you're putting the right things in. Ammonia is 0.20 molar squared divided by nitrogen, which is 0.10 molar, and then multiplied by hydrogen, which is 0.30 molar to the power of 3. Okay, no ice chart. So we do the math on that and we get a value of 14.81. So it says there, is this mixture at equilibrium? No, it's not, because KQ is 0.4. If they were equal, Q and K, then be at equilibrium. So it's not. So we're going to answer this. So number of steps, this is 1. Number 2, we're going to say not at equilibrium. And which way will it shift in order to reach equilibrium? Well, my Q value is pretty big, but the K value is small. A smaller value means it's favoring the reactant side. So we know that it has to shift and it has to make more reactants in order to satisfy equilibrium. So it says it's not at equilibrium. We're going to shift to make more reactants. And that's all you got to do with reaction quotient.